holes I think is interesting.
You may be beyond. You may be
No,
beyond.
This is a very simple point of view. In any system of matter, there's a part of the total energy is gravitational potential energy.
Yeah.
All right. As the matter gets closer and closer together, the portion of the total energy that's in the gravitational field increases.
Yes, it does.
Even no matter what the mass is, if they were point masses, you could never get them all the way together because there's not enough energy.
Yeah, you're right.
There's not enough rest, so there's an absolute limit on how close you can get the matter together.
You're right.
And so I think of a black hole as the state of matter in which all of the rest mass of the system is tied up in the gravitational field. And what I think, here's one of the aspects of my cosmic recycling theory that there's some aspects that I think are right, and later on I'll tell you about what I know is wrong.
Yeah, okay.
But, we absolutely need something that violates the second law of thermodynamics to have an eternal universe. And I believe that's black holes. When black holes take in particles with all these degrees of freedom, they get converted to pure gravitational energy and they lose entropy.
Yes, they do.
And so then the only thing left, the other really big piece, is you need a way to get the matter back out of the black hole.
Yes, you do.
And Einstein wrote a paper in 1939 talking about how impossible it was for multiple black holes to join together into a big black hole. You ever read that paper?
No, I haven't read that one, which of course now we see is incorrect. We see this all the time now.
But the thing is, how do you conserve angular momentum?
Oh, this is a great question.
So,
yeah, right.
you know about
right.
curved black holes?
Sure, spin.
Well,
Something they're trying to measure.
my friend Dwayne,
Yeah.
he was a manic depressive, he killed himself, but he was brilliant. He saw the need for a curved black hole to conserve angular momentum, and then we looked it up and we found out this is well known.
Yeah. So,
And I believe those jets are mainly matter falling into a curved black hole.
yeah, that's one way is you can actually, the jets that come off black holes are actually one way to get rid of the angular momentum of stuff that's coming in. And
Right.
That's absolutely true.
Yeah.
Right.
So,
You would come back to the entropy question. This is what bothered Stephen Hawking
Yeah.
for most of his career, one of his big claims to fame. I'm not going to claim to be an expert on this, but I can try to describe it. He actually worked out something, and you're right about many things here. One is, you cannot take two particles and put them infinitely close together in classical or general relativity
neither one allows.
without infinities, right?
Yes, that's right.
Right, so something has to give, and it's either going to be gravity or it's going to be quantum mechanics, and nobody's figured out how to marry those two together. Stephen Hawking did a lot of seminal work on this. One of them has to give. It happens at something called the Planck scale, which is basically if you take the fundamental constants of gravity, the Heisenberg constant, the Planck constant associated with quantum mechanics and the speed of light, and you fool us around and come up with a scale, a length scale, something called the Planck scale. And it's got to be around there where the effects of quantum mechanics become relevant for gravity. So that's sort of that limiting distance where we just have no idea what goes on beyond that. A lot of people think string theory is the answer, but they don't have any way to test it yet. And then coming back to entropy, so Hawking, one of his contributions was to add to that second law of thermodynamics that the surface of black holes must have entropy. And in fact, the amount of entropy they have goes as the surface area of a sphere with a radius of the Schwarzschild radius for a non-spinning black hole.
Yeah, the event horizon.
Yeah, exactly. So that area increases, the entropy is proportional to that overall surface area. So as you increase the Schwarzschild radius, the amount of entropy is also going up. And then, of course, this leads right into then the Hawking radiation issue as well.
I never did understand Hawking radiation.
Yeah, that one's, I can give you a quick, we do that a little bit. So this is, I look at this as a semi-classical way to describe whatever quantum gravity has to be. So we got general relativity, which works to infinitely well. We've yet to make a measurement where general relativity does not work. Quantum mechanics, same problem. We make excellent predictions, we can make all these measurements, and the theory always works. But we know they can't work in this, when you get down to this Planck scale. So the idea is the following, if you believe quantum mechanics, then we have Heisenberg's uncertainty principle, says pairs of particles can pop in and out of existence all the time, right?
Right.
And even a photon, two photons can be there, one can be the particle, one can be the antiparticle. And they can come into existence and annihilate, and as long as they do that in a short enough period of time, then you don't violate the uncertainty principle. So Hawking says, what if this happens, and we know this happens, right? Because there's something called the Casimir effect, which you may know about.
I've heard of it, but
Yeah, okay, so if you take two metal plates and you put them really close together, then what happens is you restrict the particles that can form between the two plates, because they have to adhere to the boundary conditions that their wavelengths can't be longer than the length between the plates. So when I do that, I limit the amount of what we call these virtual particles. There are fewer of them between the plates, but there are more of them out here outside the plates. And so it actually causes a pressure trying to push the plates together, and that's been measured.
wow.
And I had a student once who worked for Johnson Space Flight Center, where she said NASA's actually paying people to try to figure out if you could shape the plates in a certain way, could you actually get a positive vector out of that from this effect? Because if you do, then that's a propulsion system that would extract energy from the vacuum.
That's cool.
Right, so that's just one application. That's
And
a real effect.
so in Hawking's theory, you get these
Yeah.
virtual particles
Yep.
forming along the event horizon,
Yes.
and one gets captured, the other doesn't.
That's exactly right. And so the one that gets captured falls into the black hole. The other one now no longer sees as antiparticle and streams away, and the black hole appears to radiate that new particle. The weirder part is, because that particle is coming away from the black hole, even though it absorbed one particle, loses mass. So that energy is still conserved. And so this is the whole idea behind black holes evaporating, for example. Now,
But I think evaporation's probably one process, but the other process is black hole collisions, and I do believe that black hole collisions can explain spiral arm galaxies. You know about the fact that spiral arm galaxies have more matter at the outer perimeter.
Yeah, that's right.
I think that small black holes that are too small to form spontaneously are common throughout the universe.
Well, that is a theory for dark matter. That is one theory of dark
And
matter.
I think we've got at least 3 of them right here in our solar system. One in the core of the sun, one at the core of Jupiter, one at the core of Saturn.
What makes you say that?
Well, the neutrino flux problem up from the sun was the
Yeah.
first thing that got me going on that, and that was not original. I can't remember where I picked that idea up.
Yeah, okay, but that's a real problem, and there is a solution to that problem. That
Yeah, that is involving neutrinos changing to a different form, which
That's exactly
somehow
right.
sounds like bullshit to me.
It's okay, you see this happen in other experiments. It does, so the thing is, like, if you make one prediction, and then of course you have to go test it somewhere else, and they've seen neutrinos oscillate now. They change flavor.
But are they changing? It doesn't really explain the entire problem. Originally, they thought only 10% of the energy of the sun could be explained in terms of fusion. And so maybe now they can explain 60%, but that doesn't rule out a small black hole in the middle either.
No, and you're right, I don't think, we'd have to think really hard about what the signature of the small black hole would be.
But I don't think we could find a signature, because what I think is you get a balancing of radiation pressure. Because, a black hole, the mass of the Earth would be about a pea, the size of a pea in event horizon.
Mass of the Earth. For the
So-
sun, it's a couple kilometers, as I recall. Maybe a kilometer, right? If
Well,
the mass of the sun would be a kilometer or so.
See, you've looked at the Schwarzschild equation, right? The most amazing thing to me is that the event horizon diameter scales linearly with the mass.
Yes.
That means that the average density of the event horizon is going down.
Yes.
And somebody I know from Harvard Smithsonian,
Yeah.
I don't know if he ever published this, but in grad school he thought that if you apply that to the known mass of the universe,
Yeah, it actually works.
yeah, you get that.
Yeah, you do. People have speculated that maybe we're inside one giant
Yeah,
black hole.
right.
Absolutely.
Even us.
Yeah. The whole universe is.
Oh,
every
I
time you
see.
create a black hole, you spawn a new universe. This has been postulated. As,
Yeah, it's a
kind of
weird.
creepy all of a sudden.
Sounds good to me, yeah.
Right.
So, I do think that cosmology is tainted by theology.
Yeah.
I do.
You mean that people want the cosmology to work within the theology?
Exactly. That guy Georges Lemaitre definitely was a victim of that.
He was and I remember, I think Einstein quoted something like, he told Lemaitre, your mathematics is excellent, your physics is abominable. And Lemaitre is the one who predicted the origin of the universe.
Hey,
My son
Casey.
Casey.
Hi, Casey.
Yeah, Georges Lemaitre
Yeah.
was a Jesuit priest.
Jesuit priest solved Einstein's general relativity equations for the universe and decided that, well, one outcome is the universe must be expanding or contracting
Yeah,
unless you insert this cosmological constant that Einstein did,
yeah.
which then makes it stable, but it's actually an unstable solution. It's like standing a pencil straight up.
Yes,
It's
exactly.
stable, but if you wobble it at all, it'll fall one way or the
Yeah,
other.
a little
It has to collapse or expand. And that's the problem I give my undergraduates to work through when they see the equation, because I like that one. So Einstein blew that, and he admitted that. That was
Yeah,
a
he
huge
did,
mistake,
he
yeah.
did. It's,
Yeah.
it's a mind-boggling, you know, aesthetics was the word that I was looking for, is that ultimately cosmology is motivated by aesthetics, you know, God, you know.
Confirmation
Einstein-
bias, yeah, I agree.
Einstein said God doesn't play dice with the universe,
Right, that's right.
but maybe he does, you know?
Yes, this is why people think this multiverse theory might be correct.
Yeah, I'm very fond of the multiverse theory
Yeah.
because in principle, it makes room for magicians.
Why is that?
Well, suppose that everything that can happen does happen. That's the essence of the multiverse theory.
That's another,
If it's allowed by quantum mechanics, then there's a version of the future where that happens.
this is part
Now,
of it, it's another
if you believe
interpretation
there's
of
only
quantum
one
mechanics.
future,
Yeah.
and you think you can change the future of the whole world, then you're an egomaniac. However, if there are trillions and trillions of futures, it looks a little bit different, because now instead of changing the one and only universe, you as the magician are choosing which branch of reality you're gonna walk in.
And these multiverse, it wouldn't be universe, wait, would it just be multiverse? I mean,
A
universe is just one.
multiverse, well, the universe would be the
Right.
sum of all the
Yeah, but
multiverses.
anyway, if there's multiple ones, are they layered over top of one another, or are they go so far and then you move into the
Well,
next
my
one?
interpretation, you know about some of the fundamental particle theories that predict the vacuum energy as being like 10 to the 35 joules per.
Oh, sure, yeah, right.
What if that's real? And basically, all that matter gets parsed between all of the realistic multiverses.
I don't know enough to say one way or the other about it, except that matter has to stay confined within the three spatial dimensions we see. But maybe this is because that's the only way we
But
can see
maybe
it.
the three spatial dimensions are different for each multiverse.
Well, that's very possible, in fact, probably likely.
And so if that was the case, you would expect minute fluctuations in the Planck constant, according to how many multiverses there were locally.
You may know more about it than I do.
Minute fluctuations of time.
That's the problem, like the light decay that's implied by my Big Bang theory.
This would be sort of, you're seeing corrections or aspects of, at the string scale, in showing up at the Planck scale, is what you're really talking about. So they're beyond what we could actually detect,
Mhm.
but they would be impacting our universe from basically the exchange of information between those universes at that level.
Yeah, I wanted to pick up on, you know, I said that there
Yeah.
are probably 3 small black holes in our solar
Yeah.
system. I wanted to explain that.
Mm-hmm.
Our viewers may not realize that the heat flux coming from Jupiter and Saturn are about twice as high as they ought to be if all the heat came from the sun.
Yeah, that's right.
So, where did it come from?
Well, okay,
It can't be from nuclear fusion. The
No.
pressure inside Jupiter isn't high enough.
right. But it can be leftover heat from their collapse.
I don't believe that. It's been too long. I
Yeah,
think,
it's been 4 billion years.
yeah,
Right.
come on. I don't believe it. But,
Why don't you believe it? I thought we were
well,
talking- saying.
look, I should go and actually do the calculations. And if it's true, I could accept that. But my favorite theory is,
Okay.
since we live in a universe in which there are lots and lots of small black holes, you would expect that occasionally one would get stuck inside of a planet or a sun.
Yes.
And if you have 2 inside of a sun, they're definitely gonna find each other, and you're only gonna have 1. You never have more than 1
Yeah,
inside of
okay.
any planet.
They'll collide.
They will have to do that. However, Jupiter and Saturn, they wouldn't have the size you know, a pea-sized black hole inside of Jupiter
Yeah.
would be producing enormous floods of gamma radiation.
As material heats up on its way in.
Yeah, exactly. It goes to, you know, close to the speed of light.
Yeah.
And, you know, I saw that estimate somewhere in a Scientific American article.
Yeah,
I
yeah.
can't cite, but
No, it's true, and it would be, I mean, the analogy is, in the fusion process in the sun, you convert a small fraction of the rest mass to energy.
it's about 1%.
Right, that, exactly correct.
And so 40%
yes.
implies that the sun could be a lot older than we think it is, because our age estimates are based on
Yeah.
the heat output, right?
You're right about that, that's exactly right. Well, the age estimates are based on the heat output, but it's also measured from radioactive elements in the solar system. So this is one of the scientific
But I
justifications.
thought the radioactive elements were the byproducts of previous supernovas.
Yeah, that's right, that's right.
The
So if
age
you
of our
look at-
solar system is, I understand, in other words,
Yeah.
if you had something like a uranium crystal, it would have converted.
It would do downgraded to whatever.
I mean, that's how the oldest rocks on Earth are dated.
Right, and they'd also, one of the scientific justifications to bring moon rocks back was to age date those as well, and it's done since with asteroids as well. And the answer is always around 4.5 billion years. That's actually where they get the most precise measurement, it's not just from the sun.
Well, that could, it's just,
Right.
we don't really know that the cloud that was orbiting the sun was formed at the same time the sun was formed.
Now, you're right about that.
We
So-
do know that the cloud around but if we, let's say that there was a nearby supernova that would, and some of that got trapped in our gravitational field. Of course, it's hard to see exactly how it gets trapped.
Sure. Well, it does. It would get trapped in, you're right, it would get trapped in the gas nebula that then collapses to form the solar system, right? That's the working theory.
Yeah,
And we
I
see
mean,
that going on
I don't have
elsewhere.
any strong objection to any of that, but,
Yeah.
you know, if the sun's power is coming from 50% or more from a black hole, that might mean the sun will burn a lot longer.
You're right. It has a lot more energy reserves available for it.
Yeah.
That is correct.
I have a real elementary question. I
Yeah.
always thought that if you got too close to a black hole, you get sucked into it.
That's a great question.
So why is the sun
If you took the sun,
sucked into
and,
the
well, it is slowly, he's saying, so you're building up and the matter very slowly is falling in, and the heat from that is empowering the sun.
So if you say if Jupiter and Saturn had these, it would be the same.
Black holes are,
notion.
in some
Yeah.
sense, just mass,
It's-
right? So if you
there's
took, yeah.
It's called radiation pressure. There's,
Yeah.
radiation exerts a momentum force. We didn't normally think of it as quite small.
Yeah. Well, it is, but it's also it's rather unstable because the pressure is increasing as the temperature to the fourth power. So a small change in temperature causes a huge spike in pressure, and you do see this in some aspects of stellar evolution. Even in the core of the sun, assuming there's no black hole, it's actually not radiation pressure that's dominating, it's really just the ideal gas law, in which case the pressure increases as the temperature.
Well, now,
they go up and
that's
down.
not quite true, because as you know, the ideal gas law applies to atoms and there
Yes, it
aren't
does.
atoms.
Well, they could be ions, it's okay.
Really? Well, it's the same idea, but I'm just saying that the Boltzmann distribution would not be the distribution of energy.
Fair enough, it's the approximation that fits, and the radiation pressure, even at the center of the sun, is not the driving force. Right, in that case. If it was, the sun would be oscillating a lot more because the pressure would increase, the small change in temperature would cause the pressure to spike and the outer layers of the sun would blow off until the pressure cooler cooled down and then the whole thing would kind of oscillate. And we do see cases of this, especially stars at the end of their lives, when this is happening. They are too luminous and they're blowing off material.
You wanna hear one of my science fiction ideas?
Really?
Okay.
One question, 2 o'clock minutes, one question that somebody asked is, can or does space have mass? Also, Cowabunga, thanks for the follow. Can or does space have mass?
So in that sense, I'm kind of read alarm going on. Okay.
It's pills for me.
Oh, gotcha. Okay.
Yeah.
So does space have mass?
Yeah.
It's a great question. So, oh man, mass is how I think about it, and not everybody might think about it this way. Because Einstein said E equals mc squared, and that falls out of special relativity. Mass and energy are interchangeable. They're just different aspects of the same thing, and you have to include the rest mass of an object when you're talking about the total energy that a system might have. That falls out of special relativity. And so mass, you can think of as the intrinsic amount of energy that what we call matter carries around. So a proton carries around a certain amount of rest mass. Electron carries around a certain amount of rest mass. So in that sense, empty space would not carry any mass. But it does carry energy from these virtual particles that pop in and out of existence. So when they pop in and out of existence, they do have temporarily a small amount of mass. And so that means there is some effect overall. There's no true vacuum, and the vacuum does have this energy associated with this effect. People think that may be related to dark energy. The jury's still out on that one.
Sometimes called 0-point energy.
Yeah, right. That's good.
There are a lot of people in the world that believe that it's somehow possible to harvest 0-point energy.
Yeah, if we can, it would be an infinite amount of energy available to us. I mean, well, just within the context of the universe, that you're extracting energy from the vacuum itself.
Yeah. That would be cool.
That would be
the
cool.
biggest breakthrough ever.
Yes, it
Then we could maybe have a warp drive.
Well,
We can get to the end of these.
in the
the
sense
outer
that a
limits of
spaceship is
this
just being
universe.
powered. Yeah, a spaceship would be powered by space itself.
So how, now, you're gonna say something about science fiction, but before you do, I have a science fiction.
Oh, well, this is definitely a tangent, but imagine some future where they discover a certain form of matter that we don't know about today, which I call a plasma crystal.
Okay. Okay.
Now, the density in the core of the sun is way higher than any known matter.
Yeah.
Now, what if that, given enough time, that you'd form a different state of matter where some of the electron shells get squeezed out? You have a metal where instead of just the outer electron layers being involved in metallic bonding, you have this condensed form of matter. It might have, 1,000,000 tons per square centimeter, cubic centimeter, or
Yeah, whatever.
whatever the number is. Probably would be something more moderate than that, but it would have to be just a delicate place. And they would only be found in stars that died, say, 100 billion years ago.
Yeah,
So it's
okay.
kind of contingent on my theory.
Yeah. So we're talking about, the innards of like a white dwarf star.
Yeah, but one that finally cooled off, and it wasn't
Ah,
massive enough to become
okay.
a neutron star. You see what I
Sure.
mean?
Yeah. Right. You're right,
So
like,
this
yeah.
becomes the most precious thing in the universe, because the only way you can make it is inside of a dead star.
How do we go
And
get
so
it?
there's an industry around mining it, and to do it, you gotta blow up the dead star into pieces.
And like extract it. But I think when you look, science fiction, you have some literary license. When you blow up the star, you would release gravity in some way, which is what's holding it in the superbound.
Well, but maybe
state.
not.
Maybe not.
Gravity maybe has to hold it while it crystallizes into a form of
Oh, I
crystal
see.
we don't know.
And then sort of some new state of matter. That's
Exactly,
beyond.
a plasma crystal.
Okay.
And
I
wouldn't that be great?
could not debate you on that one. That's a good idea.
So, but we have to go at warp speed to be able to get to where the waste
Good
star
point.
is.
Yeah. Right. So that's a
Yeah,
problem to
star.
solve. Right. Okay.
That's where you need Han Solo and the Millennium Falcon.
That's right.
Something of that nature.
And so you wanna hear about why I quit working on my theory?
Yeah. Why?
I made a testable prediction that was wrong. And
Okay.
I was depressed for 2 months.
I think that's called theoretical physics syndrome.
So you'll totally understand this.
Yeah.
There's a characteristic time period for a certain class of supernovas. And
Yeah.
those supernovas are so bright that you can detect them even in distant galaxies.
Yeah.
So, if the Big Bang theory is right, the time signature of those supernovas should be stretched exactly proportional to the redshift of light. And according to my tired light theory, it wouldn't have been that
I
way.
think that's right.
And
Yeah.
and when I made that prediction, then I went looking and found out it had already been measured, and I was devastated.
Yeah.
But that's actually how science goes. You're supposed to make up theories.
Well, the thing is that I now know that my cosmic recycling theory can't be right down to the full details, but I think parts of it might be right. Like black hole collisions leading to galaxies, I thought of that on my own, and I think other people have been pursuing it since.
No, I think you're really delving into what are these unanswered questions. What is dark matter?
Yeah.
and there's no one around who knows this. All we see is this gravitational effect on large scales,
Yeah.
and we have a lot of theories behind it.
Yeah,
but, you know.
it could be that 90% of the matter in the universe is small black holes, or basically non-radiating black holes.
You're right about that.
A black hole in interstellar space would be completely invisible unless it was so massive that it had gravitational lensing you could spot.
Yeah, and people have actually looked for those, but you're right, they'd have to be big, they'd have to be massive enough.
Right.
So like you said, so if it passes in front of a background star,
Yeah.
the star's light gets magnified, and they haven't seen those.
Yeah.
But all that does is limit the size of the black holes.
Yeah, I mean, you could eventually detect it, let's say they're whizzing around in one, it could come right through our solar system and it probably would go right through a planet and not even get stopped.
Yeah, you're right. they're
And
too
wouldn't
small.
disrupt life on the planet if it was.
Well,
a
you know what would
planet
happen,
would
I've
be-
thought about that, let's say it's an Earth mass black hole, event horizon 1 millimeter across, it hits, say, the Earth. It would probably be slowed down a little bit, but not very much.
Oh, it's pretty dense, it's like a bullet going through an apple.
Right, it's gonna shoot right through, and at the entry and exit, there's gonna be a burst of gamma radiation.
Sure, right.
How would that manifest, say it happened here, how would that manifest?
Well, we would basically, it would seem like there was a nuclear detonation on one side of the Earth, and then there'd be a nuclear detonation a fraction of a second later on the other side of the Earth.
So it would be a big event. It would
I
be
just
small.
calculate how much energy we would release during the
So
collision.
somebody would blame
Calculate.
Kim in North Korea, and then they blame Trump for responding.
Yeah, but I don't think you would get the nuclear products. For those instance, like, you know, we have
Yeah.
satellites looking for these weird isotopes in the atmosphere over North Korea.
Well, you wouldn't see any of that.
Right, you wouldn't see any of that.
You
just
would
see
probably
gamma
find all kinds of rearranged nuclei, though, it would be so hot, you know?
Yeah,
It'd be like the kind of, more similar to the kind of stuff you would see at the CERN collision reactor, what do they call that thing?
yeah, the LHC, the
Yeah.
Large Hadron Collider, right.
You get all kinds of stuff spewing out that would be vaguely
Yeah,
like
in
that.
fact, there are people who get concerned that by smashing these particles together near the speed of light, you will create a small black hole which will utterly annihilate the rest of the planet.
But
In fact,
that
this
part's
is-
stupid, it would just sink
Yeah.
to the core and it would very, very slowly grow.
Sure, except this is also one of the explanations for why we haven't found intelligent life. The explanation is once they get to this point where they can make little black holes, they annihilate themselves.
Oh, that's great. Oh, here's one of my, this goes over into the range of biology.
Okay.
If we had a supernova sufficiently close to the Earth, we could have pretty much sterilized life on Earth.
Yeah, you're right about that, and that is something that people worry about.
People
especially when
don't-
these gamma
you know,
reverse things.
The Permian, you know about the Permian extinction?
There were 5 major extinctions throughout history.
I think the Permian was about 500 million years ago, and it, like, most of the species except for stuff
Right.
living in the ocean died out.
Right, that was bigger. It was deep in the ocean where life survived. Is that the-
Right,
Okay.
and that really fits with the idea of either a gamma ray, well, it wouldn't be a gamma ray burst because they're too short and half of the Earth would have
Yeah.
survived. It has to be something to
But you
last.
sterilize the atmosphere in that process, right? But that's what you're saying. You have to leave. It has to be just balanced enough that you kill everything on the surface, but you don't destroy life on the whole planet.
Well, you know, gamma radiation, even the most energetic gamma radiation doesn't penetrate to the bottom of the ocean.
Yeah, right. The ocean's pretty dense.
It is. I think most gamma radiation is probably absorbed in about 30 feet of ocean.
Okay.
And, you know, those deep sea vents would have been repositories for life.
Yeah, right. In fact, they think the oldest DNA on the planet may be the bacteria around those vents. Right.
Which makes it look good for Europa, right?
Yes, it does. Make it look good for your Yeah, that is on NASA's bucket list. They're heading there.
Yeah, I'm all for that one.
Yeah, right.
Tell us more about Europa, what's that mean?
Europa is one of the big moons of Jupiter.
Oh, okay.
It's covered in ice, there's an ice layer, but the satellites that we've launched, they do density measurements for gravity, and they've determined the density underneath is more consistent with water. There's probably a huge, couple kilometers thick shell of ice over the whole planet with liquid water underneath.
So
And
there
where
could be
there's
life
liquid
in there.
water, there's life, and there are cracks in the ice on the surface, which is, I think, caused by the tidal stressing of Jupiter. Our moon causes tides here on the Earth. Jupiter causes tides on its moons, and it squeezes and contracts them as they go around it, which cracks the ice, but would also generate a source of heat for maybe life to
Keeping it
extract energy from.
Generally, causing life to generate.
Right, in fact, Io, the moon's called Io, is gonna name it for some Greek, is so tidally stressed, it's the most volcanically active object in the solar system. It's close enough to Jupiter that the tidal field is so strong.
Gravity.
Right.
Alright.
This things where ring systems come from. As the moons stray too close to the planet, the tidal forces from the planet rip them apart and they become rings. One of the theories, probably right.
So when I was trying to work out the idea that light decays, my first idea was that it's a simple exponential decay.
Okay.
And it's easy to calculate what exponential decay would give you the redshift. And it is about 1 part in 10 to the 18th
Okay.
per second of decay.
Okay.
Well, that implies that the photon decaying off would be exceedingly low energy, even from a gamma ray particle.
Yeah, right.
So it can't be the direct source of the cosmic background radiation.
Yeah,
Instead, the wavelength of that light would be greater than the size of the Earth, in a way of thinking.
Sure.
But maybe that then re-equilibrates and gives you the cosmic background radiation. That was the crux of what I was thinking.
Well, so that's, and I know these theories have been out there mostly to explain exactly that. What is the origin of this heat? You probably know Fred Hoyle did not,
Hoyle was the one that coined the phrase, the Big Bang Theory.
That's right. He was an excellent communicator, despised the idea of a hot Big Bang Theory. And at his time, the Big Bang Theory could not explain vast regions of physics and astrophysics.
Right.
And so Hoyle, I always feel like is the most brilliant physicist never to win the Nobel Prize.
Yeah.
I think it's because he was on the wrong side of the Big Bang argument. Right?
Or maybe he was on the right side, but I don't like his
Fair enough, okay.
I mean, I don't like his theory of the eternal fountain, but
No, but the work he did with Burbage and Fowler on nucleosynthesis in stars is still what we teach, and it's all correct.
yes.
I mean, just fundamental stuff that should have been awarded the Nobel Prize in my opinion. And nevertheless, so they could explain the expansion of the universe. I love this. We teach this in class. So the expansion of the universe, Hoyle absolutely agreed with. You can't refute that. And he would explain it as, well, there's 2 options. If the universe is expanding, then at some point in the past it'll have to be microscopic in size.
Right.
And that gives rise to this hot Big Bang idea. The other one is, well, let's just say the universe has always been in a steady state, but new matter is spontaneously created at a rate of 1 new proton in every 6 foot by 6 foot by 6 foot box per billion years. And if that's the matter creation rate, then the universe simply expands to make room for the new matter, and that would explain the expansion. And that's absolutely how Hoyle explained this. The difference is that then says there was no time in the past when you would have a hot state, which would then give rise to the cosmic microwave background radiation, right? And so I think these tired light theories then give rise also to a cosmic microwave background theory. The difference is, these are important things to state. I always feel like science needs people kind of challenging the paradigm. We've seen paradigm shifts in the past in astronomy. Galileo is a good example. The thing that goes next is, okay, when you look deeper at the cosmic microwave background, there are fluctuations in the spectrum, right? And if you look around the sky, you see these fluctuations, and there are 1 part in 100,000. And these are now hypothesized to be the leftover quantum fluctuations from the vacuum from when, let's say, inflation occurred. That's the idea. If you take the spectrum of those fluctuations, you have a few big fluctuations, some smaller fluctuations, drop them into a supercomputer, and allow those fluctuations, if you have a little more matter at the time of the cosmic microwave background, they grow under gravity, and if you have less, they lose mass. And the big ones grow and they grow and they grow, and the statistics from that exactly reproduces the distribution of galaxies we see in the sky. And so you can map that over 14 billion years, if it's really just the fluctuations in the cosmic microwave background with gravity, and then left to its own devices for 14 billion years. And we've measured that now here, we've measured it at different times in the past, and we can see it just maps so nicely. So all of that fits together really well, which I think gives more credence to this idea that there was actually a Big Bang at some point. Or at least you have to be able to explain this fluctuation, in addition to just the hot Big Bang idea.
Well, if it was just a stochastic thing, in other words, if the universe is infinite and eternal,
Yeah,
you would never have no fluctuations. There would be fluctuations.
sure.
So, and I understand also that the intergalactic, deep space incidence of lithium-6, lithium-7
Yeah, that's the
fits
problem.
very nicely with the Big Bang Theory.
Mostly.
But,
Yeah.
you see, that same kind of physics could have occurred during black hole collisions. If black hole collisions are the method of recycling.
If there are ways to do it, then I think that's a theory that should be pursued.
Anyway,
Yeah.
I gave up on the CBR when I had that testable prediction. Since then, I've been thinking that, why in the world should I think that the time domain is special? In other words, if something's decaying, why doesn't time decay too?
Oh, yeah, now you're good. Now this is good. Yeah, right.
But I never was that good at math. I'm really glad to know that Einstein wasn't that good at math either.
Yeah,
What do you think it would mean if time decayed? What would be the implications?
Well, it could
ramifications?
explain why the time signature of those very, very distant events gets spread out. That's the
I
immediate.
see what you're saying, like time itself actually gets stretched in some
Yeah.
other way.
Time
Yeah.
no longer, to the extent time moves at speed,
So the
it's no
cosmological-
longer moving at that speed.
The cosmological redshift is essentially a Doppler shift. You can imagine it that way. So like a train goes by and the pitch goes up and the pitch goes down, a little bit more, right? Light does the same thing with the expansion of the universe. It's two effects. It's that, if an object is here and emits something, then if it's emitting a wave, so you have a peak and a trough and a peak and a trough. You get a peak here, and then the object moves away, and then the next peak goes off, and that stretches out the wavelength between the two. That's one way to think about it. But the other effect is special relativity actually causes an additional time dilation effect, and both show up as this cosmological redshift. So that's the way that folds through in the mathematics of it. So time, like you're saying, if you have an event where you have a star explode at, it's moving at half the speed of light away from us. What happens is, if we were to observe it in our own galaxy, we would see, it has a peak to it, and then it decays back down as it explodes and then fades. When you see this in a galaxy that's moving really fast away from us, that peak rise is slower, and then the decay is slower. So the whole event is stretched out in slow motion for us. And we see that. That's actually what you're talking about. That's been observed. Right. Because you can observe this special class of star that explodes over billions of light years. They're so bright.
I mean, I think for most of us, there's two hard parts. One is
Yeah.
that kind of time frame, and then also that kind of distance.
Yeah. Right.
To where these places are. But even if there's one universe, its magnitude is beyond what I can comprehend.
Yeah. No. It's they've
Well, the
done.
thing is, that's the great thing about math.
Yeah, I know, right? Math gives you a way to express
Yeah,
this stuff.
right.
No, this is the first day of my class. We'll talk about numbers. Humans are really good at. So it's Daniel Kahneman and I've forgotten the other guy. They won the Nobel Prize for economics. They were these psychologists out of Israel.
Oh yeah, I don't know.
They wrote a great book. Daniel Kahneman wrote this great book, Thinking Fast, Thinking Slow, and it's really good about your brain. And so I've always wondered how this applies to my class and my students because I see it. And you basically have a fast-thinking brain, which is always in charge, and then your slow-thinking brain, which we always think of as a rational brain,
Yeah.
and we always think we're making these decisions. But most of the time, your fast-thinking brain makes all the decisions, and your slow-thinking brain is trying to justify why you just did what you did. And that's the crux of the book, and I apologize to Professor Kahneman because I'm sure I just butchered that in there. But they won the Nobel Prize, so they're way above me on that. But anyway, so studies have shown that humans and animals can identify numbers up to about 5 by sight. You don't have to count. You'll just look in this room and say there are 4 people in this room, right? You don't have to count that. And you go much above 5 and you can't anymore. We're really good at math, so we can subdivide the room and say, okay, there's 6 people here, 6 people here, that's 12. We're really good at that. But then if I show you a picture of 100,000 people, your brain has no way of knowing, is that 50,000, is that 75, 100? And we're talking about many people. And the best way I learned about this is that humans, I attribute this to somebody on NPR, and I've forgotten it, when they were talking about the national debt. And the way you think of it, because what does a trillion mean? Right? And we're talking about the galaxy with 100 billion stars in it, and we're talking about the universe with 100 billion galaxies, and they just stack up. And we lose it after 5. We just can't count beyond that. And they said, this is what you mean by logarithms and the scientific notation and exponents. Humans have a built-in perception of that for time. We have different units we use to communicate aspects of time. Like you would never say, as a parent, my son is 31 billion seconds old, right? But you would change that unit of time. So if you're talking about short periods of time, we say seconds. If you're talking about longer, you might say an hour. If you're talking about, we've got a day, we've got months,
So you cope with the
years, right? There's a logarithmic way to express time. And so then you can say stuff like, I always say this in my class, how many of you are 1 billion seconds old? And they all look at me, and they think about it for a long time, and somebody will, so eventually they'll pull out their calculator, and they realize that 1 billion seconds, so I'll back up, a year is 31 million seconds. What's 1 year? In fact, to a good approximation is pi, the number pi, times 10 to the 7, so 31 million. So a billion seconds is 31 and a quarter years. And so if you say, if you were to count, if I gave you a stack of money and said you can keep $1 billion if you count it $1 at a time, how long would it take you? If you didn't sleep, 31 years to do that. So you ask, well, how long is a trillion seconds? And the answer is 3,100 years. Right. Did I do that math right? 31,000 years. Yeah, sorry, that's right. 100 billion is the number of stars in the Milky Way. That's why that number jumped in my head. So it's 31,000 years to count out $1 trillion. And of course, that's
You had it for a while.
the deficit in the U.S. Right.
So when I was on this multiverse train of
Yeah,
thought, which pagans love the multiverse because it gives you power in the world. But I did this little calculation, assuming that the diameter of the universe, that the radius of the universe is 14 billion light years.
Yeah.
I split it up into 1 angstrom cubes, and I estimated, it doesn't matter how big the number is, it's still finite.
Yeah, you're right. You're right. There
And
are.
then either every one of those has one of so many kinds of particles, or nothing in it at all.
You can count up the number of protons in the universe.
Exactly, and no matter how big the number is, it's still finite.
It's still finite. That's correct. Within the visible universe, which is what you described.
Yeah.
14 billion light years in radius. Right. It's a finite number.
And so if I
Yeah.
did it again, I would probably use the Planck radius instead of
I would say certainly
instead of
not.
an angstrom or whatever, but it's still a finite number.
Yeah, sure.
So I wish I had. The thing is, I never could publish that stuff. I couldn't get it in the right kind of journals or anything like that.
Yeah.
And I think
Sometimes
parts
it's
of
hard.
what I was thinking was correct. Parts of what I was thinking
Well,
was
so for a
correct.
mainstream journal, they'll send it out for peer review, and then you got to get it by the establishment because most of them are trained in the exact same way I'm trained.
Mhm.
You know, and if you don't buy into, if you don't drink the Kool-Aid, they don't give you a PhD. So
I know that. I
Yeah.
know that.
Yeah.
So that's probably why I'm more attracted to being an inventor than a scientist.
That might be true too. Yeah.
Because inventions are real things,
Yeah.
and there's a final proof in the pudding kind of thing.
That's right, otherwise, the
Right.
sky's the limit. Otherwise, you can.
No, you gotta get tenure before you go crazy, and then you can start inventing new theories. And I always feel like it's important to push those boundaries, because there are plenty of examples in astronomy and cosmology where humanity's just been on the wrong path for so
Yeah.
long. Nobody believed the Big Bang Theory
Yeah.
forever. It was
In
very- it's a niche thing.
2011, the guy that won the chemistry Nobel
Yeah.
discovered quasi-crystalline solids, and he was mocked, and he lost his job.
Yeah,
And it's
this
just,
happened.
it's what happens all the time.
It does
Still.
happen, right. So no, it's important not to get calcified when we're doing these thoughts. Yeah, I agree with that.
So,
Right.
We need to give you about 10 or 15 minutes.
Yeah, I was
Yeah,
watching
it's-
the time.
I always feel like, okay. The science is there's always some little bit of new data that's gonna start to push people in the right direction. So there's an observation that we can't quite explain, there's quite a bit right now, dark energy, dark matter.
Yeah.
We can't explain any of those things.
The excess heat production from Saturn and Jupiter, I'd wanna look at
Okay,
it in
that's
detail.
fine, maybe you should work that out, because maybe the numbers I know are incorrect, and, it's important to keep pushing on those things,
Yeah.
right? But that, for example, would be a testable prediction from the theory that there might be black holes in the center of them. And if that's testable, then that's exactly what we should do. And it might not be testable now, but maybe we build better probes that are able to better measure the spectrum or energy coming off those planets. And then
Or like the decay of light, if it's
Yeah.
one part in 10 to the 18th per second, I think with far apart ballpark satellites with very accurate lasers between them, we might be able to test that.
Well, that's a test, that's what you should think about, those testing it, yeah.
So mostly I think about other big ideas like taking the fresh water that's melting off Greenland and moving it around the earth.
Yeah, but damn it,
I was telling
that's a
them
great
about
idea.
your idea.
That sounds like a great idea.
I mean, I just can't get myself to be excited about small ideas. I just can't do it.
Well, it's okay, and of course, on the other side of the coin, probably for inventors, is you gotta make it cost effective at some level, you know, but that's,
You
I
can
think
go
that's
a long
great
ways with
idea.
calculations, but ultimately
Yeah.
billions of dollars have gotta be deployed to really prove it.
Yeah, right, that's exactly right.
That's the problem with all my ideas.
Yeah.
We filed the patent for that invention on Friday.
Yeah.
They did.
And
For
then
moving fresh water?
I've been working on a letter to Michael Burry, do you know who he is?
No, one of these
Have you ever
billionaires?
seen-
No, that's
No.
that's Kristen Bale's character in.
Oh, it is, yeah,
What's the name of
the
that
movie, yeah, Moneyball, not Moneyball.
No,
The other one.
The-
Big
the
Short,
Short.
The Big Short.
Yeah, so that guy,
Yeah.
in the end of the movie, there's a little blurb and it says that now he's investing in water. And I thought, well, this is an out of the box thinker that might find my idea
Exactly,
interesting.
Yeah,
So the crux of that idea is,
yeah.
you've gotta move the shipping container below the surface of the earth, of this ocean because of storms. And to do that, you need to have a hell of a lot of ballast, and it turns out the world needs sand and gravel, and Greenland's got tons of sand and gravel.
Underneath the glaciers.
No, at the mouths of the rivers.
Oh, it's swept, the sediment is swept down.
Of course.
So
So,
you get the ballast and the water.
yeah, exactly. And, you know, to make any sense, you gotta have a tanker that holds at least 1 billion gallons of water.
That's a lot of water.
That's 10 times as much as the biggest tanker ever built, and utterly impossible for a surface ship.
So that's why you say it has to be underwater.
It has to be, it's gotta be neutral buoyant, and it's run by electric propellers. I did the calculations for a 1 billion gallon tanker, you only
Yeah.
need 60 megawatts to move it about.
For commercial vehicles, will they use nuclear reactors? You need
They
something,
could.
yeah.
And how would
It could
that,
be, you just have a cable running down from a surface vessel with a gas turbine, that
Oh,
would
it's
work too.
a surface ship to run it.
Yeah.
how would that compare to a pipeline, you know, somebody said, wouldn't it be better, I don't know what the better is, the best rate.
Actually, I don't think that the energy efficiency would be better for a pipeline at that scale. In any case, you've gotta overcome the viscous drag, but
Yeah.
a tanker like that would be like 40 meters across. So,
Yeah, but they can do, not aerodynamics, it must be like hydrodynamics or something.
oh yeah, it's not hard calculation
Right.
even, but the thing is that a pipe would be smaller and therefore there'd be more friction in a pipe than there is around the wall of a tanker. So, you know, my favorite idea is that it takes the form of a kind of a train. It's not a single tanker, if it's a
Yeah.
single tanker, you've gotta deliver 1 billion gallons, you gotta stop at port, you don't wanna do that.
Yeah, good point. Oh, like,
So in other words, each one might hold, say, 10,000 tons of fresh water,
you
each
just
car.
split them off as you pass the
1
port.
billion gallons is 384 10,000 ton tanker cars.
300, say it again,
384. And they'd be a long train, each one would have its own propellers, so
Okay.
you aren't transmitting a lot of force through the linkages.
Yeah, right, you have to,
When you come close to the port, you drop off the back one,
yeah, it just falls off.
and then, you know, some tow vessel takes it into port.
Yeah, right, okay.
It's totally doable.
It sounds like it, I mean, yeah, if you can make it cost effective, but if the price of fresh water starts going up,
It will. Right now, desalinated water costs between 50 cents and $4 per cubic
okay,
foot.
okay.
I don't know why the big difference, probably it's subsidized in some places,
Yeah, okay.
that's probably what it is,
Some
but you can
countries
easily
subsidize.
calculate the actual energy costs.
Yeah,
And furthermore, the lowest cost way to desalinate water is using, reverse osmosis, you
Yeah.
don't really get pure water.
yeah, okay.
then we do
That's
a
what
reverse
that is.
osmosis, don't you have, you have wastewater associated
You do.
with that. We have
Yeah.
had that in our house, it's like
Right.
5 gallons gets dumped down the drain for every
Yeah.
gallon that's
Right.
usable, would it be that bad?
No, it wouldn't be, it's more like 1 for 5 in the case of, unless you've got seawater, if you've got seawater,
Yeah.
there's much more waste.
No, but in a house it's more like 1 to 5, yeah,
Yeah.
it's a lot of water that doesn't get used,
Yeah,
that's true.
So it is, it's 2:30, guys.
Yeah, what
that's one of the big ones, is one of my big inventions, and, I have
Yeah.
these things that I fall asleep thinking about.
Yeah.
Another one that I've been thinking about since I was an undergrad in physics is kind of the Jules Verne method of launching rockets.
Oh yeah.
Well, it turns out that a lot of the energy of
Yeah.
the launch is getting the rocket up to speed of sound.
And I've heard people talk about this.
Yeah.
Like for small satellites, right?
So, the crux of my idea is you make a big mortar by using a tunnel boring machine,
Okay.
boring down into
Boring
the earth,
down, okay.
and that's how you make the barrel.
Okay. Okay.
And, I'm not looking for a muzzle velocity that's orbital, I just want a muzzle velocity that's supersonic.
Got it. And then you fire off a rocket once you get up there or
Right.
something. Yeah. Okay.
Rockets are much more efficient once they're moving fast, you
Is
understand
rock
that?
and stone the right material for the will it hold up? There's gonna be a lot of heat when you fire
No,
something.
there's a metal wall.
Okay. Okay.
But the rock and stone,
Yeah.
it cuts down the cost a great deal by having created the cavity.
I get it because you get okay.
And the pressures involved are not that high.
They're
I mean,
not.
it's a big mortar.
Yeah.
Shooting a Saturn V size rocket out only implies about 10 atmospheres.
Okay.
10 atmospheres behind the rocket, and of course you need a vacuum in front, so one of the key problems is how do you create a long...
Yeah, right. You got to seal it off, pump the air.
You've got to have a 5-kilometer evacuated tube, and then at the end, this supersonic thing's got to blow the cap off, or else you got to blow it up with high explosives.
Yeah, right. Because it's gonna. You need explosives to take off something that can hold that much vacuum behind it. Yeah.
It's doable, but it's not simple.
Right.
We're cheap.
I
And
thought
the
about
timing is important because
Imagine
if you
that,
miss that.
I, astronaut Joe
Yeah.
Blow,
Yeah.
now my job is being shot out of a cannon.
In a sealed tunnel, and you gotta hope that the tunnel opening opens just as you get to it.
I thought about that a lot. I think that the best way might be that the ceiling dome actually adheres to the front of the rocket.
Well, that's something you'd imagine if you have a tough enough it's got
Carbon composite.
carbon
probably.
composite. Okay. But then you gotta be able. It's gotta be able to break away when. the
Yeah, it's got to
rocket
be
hits
able to
it.
break
Yeah.
away, but
And
because of the,
instantaneously, like it can't stretch or rip.
it's really no problem because remember there's a vacuum and you could have an
Yeah.
O-ring seal and it's
Yeah,
only
it's
gonna,
sucked
it's
in.
gonna be sealed because of all that force.
Right.
But as soon as the force reverses, it just breaks away. It's
So
not good here.
wouldn't want to pull. Wouldn't the atmosphere push it in?
Well,
Yeah.
no, it's got a huge amount of momentum at that point. It's just like as if it was a rocket that had been launched from.
Yeah. All right.
The atmosphere is pushing back on a rocket.
Yeah.
It's doable.
Sure.
It is incredible to think about how much power.
So I like to find targets. Michael Burry's my target on the Greenland supertanker, the submarine supertanker.
Micro brewery.
So Michael Burry, the guy.
Oh,
from-
Michael Burry. I'm sorry.
And
Microbrewery.
Elon.
Yeah, I was like, wait, what?
No, Elon Musk is my target on the rocket launcher.
Yeah,
because
he might
has-
go for that.
Well, he's into
Yeah.
that stuff. Yeah.
And he's also got this new thing. They call it the Boring Company. You know about that?
No,
No, he's-
boring.
Yeah.
Mining. Is it?
No, it's all about these tunnel boring machines. He thinks that we can make them 10 times cheaper, then we can move a lot of the traffic in the cities below the surface.
Oh, I did hear something about that. Okay.
He thinks like you do.
He does.
Yeah.
I would,
Yeah,
I'd have
obviously,
a great
Chris.
time meeting him.
Yeah.
I don't have that superstar syndrome thing. I don't think I would treat him any different than anybody else, really.
Yeah.
Yeah, the challenge is just getting his time, getting.
Yeah, I know,
attention.
But I keep trying. I mean, back when I was an entrepreneur, I made a habit of writing a letter to a famous person every week.
Okay.
Al Gore, that guy from Virgin Galactic,
Yeah.
a
Sure.
lot
Oh,
of
yeah,
senators and
Branson,
congressmen.
Richard
Yeah.
Branson.
Right.
I never scored any of those guys, although I did have a meeting with the head of FERC, Federal Energy Regulatory Commission.
Okay.
And I met the CEO of Hydro-Quebec.
Okay.
I was pretty good at getting high-level meetings, but never could pull a deal together.
That's always the challenge.
It is hard.
Yeah.
Oh, yeah, particularly when you're thinking big thoughts in a way that's so out of the box.
Well, but are those guys gonna wanna see what the end game is, like what's the final product and return on investment, or is that not?
Yeah, the thing is that
how much is being asked
what
for.
venture capitalists told me about my L pipe, which is another one of my big ideas, too big and it's too long-term for venture capital. It's gotta be governments that do it.
Okay, venture capitalists need something on like a shorter time frame than the
Yeah.
government's willing to go for.
So, actually, my version of how to make the L pipe and the supergrid move forward is I gotta reach Xi Jinping and Vladimir Putin.
Guys who
You
have
know, there are
decades.
these sovereign, I don't know if you ever thought of these sovereign wealth funds, you know.
I
like,
have, the
including
Norwegian
Arab
Sovereign Health
yeah.
Fund was one of my targets, and I was very frustrated because when I was at Alevo, I wanted to pursue that.
Yeah.
And the owner of the company, the guy that founded the company was from Norway, and he kept pulling me back.
Cause those are huge sources of funds.
Yeah.
You know, and the Norwegian Sovereign Wealth Fund overtly says they wanna promote green technology.
Yeah, I think that
Yeah,
was
yeah, right, exactly.
Or the Middle Eastern countries who are desperate for fresh water. You know, the UAE has a huge sovereign
Yeah.
wealth fund. Qatar.
You know, I'm trying to put together, I gotta have a team, I can't do all this by myself.
Yeah, sure.
It's a matter of getting a quorum, you know, you gotta have a quorum before you can start pursuing these
Right.
big ideas. And the L-pipe could have been my first big success, but I traded away my patent rights in return for $2 million worth of stock, and then the company went broke, and now the patents are owned by somebody else.
Switzerland or Russia or somewhere. Switzerland.
Yeah, the guy that controls it is Dmitry Ryabovlev, he's on that list of tycoons that aren't allowed in the US.
Really? Jeez, alright, so somebody with a lot of money.
He's the guy that bought a house from Trump for $48 million that Trump had paid $8 million for just a few years earlier.
That's not suspicious.
A little bit suspicious. That's a way to launder money, and
Yeah, it
actually
is a way to launder
Trump was
money.
just about to go bankrupt. It was the 2008 crash. Everybody was losing money on real estate, and he made like a fourfold profit, just enough to keep him out of
Thanks
bankruptcy.
to some people from other countries.
We better go.
Alright,
Anyway, it was great fun.
this is
Casey.
great, yeah, I
Thank
appreciate
you.
it, Roger, so thank you.
We'll send you a link to the Twitch stream.
Yeah, sure.
See
You
yourself.
should have a look at it.
I might, actually, you know, you never know. Something will come up,
Alright,
so.
sorry we gotta go.
Yeah.
Our wife.
Well, you
my
got a
wife
copy
is
of my
fine.
cosmic recycling theory probably over a
Do
year
have to
ago.
read it. I know. All right. So
Now
my
you-
friends,
now
I
you
get a
know.
lot of those sent to my inbox.
I'm sure you do.
But
But
I
If you
appreciate
can't
talking to you
find it,
there.
I'll at least follow, but I can find your email
Yeah, I
from
appreciate
the
that.
website.
You know.
Thank you.
Good to see ya.
Thank you,
It's
Joe,
good to
for
see
sharing
you.
your family a little
We'll
bit with
see
me.
you.
Nice to meet you, man.
See you next time. Well,
Appreciate your help and
I
everything.
Absolutely,
man.
picked the color for you.
Oh, that's
Okay, color. It's
beautiful.
just not as big as
You
I
know,
thought it
a
would be.
prayer shawl is something very precious. I have many
Yeah.
girlfriends